Perfect. Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is a PhD student here in the Computer Science Department, Rahul Potharaju, and his topic is delivering always-on services despite flaky network infrastructure. So, Rahul?
Thank you, Randy. Good evening, everyone. Again, my name is Rahul Potharaju, and I'm a PhD candidate here. Today, I'm going to talk about our work on improving network reliability for cloud services. Our agenda was twofold when we started off this research. First, when a service goes down, there is little visibility in where the problem lies. Is it the application? Is it the server? Or is it the network? Now, application owners would typically say their servers are just fine, so the problem must lie with the network. Now, network operators, on the other hand, would say their network is healthy, so the problem must be with the application. The crux is the service is down, and no one has a clue what's going on. Therefore, our first goal is to provide visibility into how network failures can affect services. My second goal is to learn from our mistakes and improve both service reliability and network management. I've tried to put this talk fairly accessible for a lot of general audience, but if you do have questions, just feel free to stop me at any point in time. Let me start my talk by acknowledging my PhD advisor, Professor Christina Potharaju, my mentor, Dr. Navindu Jain from Microsoft Research, my co-authors, and my family without whom this research would not have been possible in the first place. And I'd like to also extend my special thanks to Microsoft Research for providing me with numerous opportunities in the last couple of years to work with them and build this whole research. Having said that, let's get started. Let us take a quick look at how reliable cloud services are today. An Amazon outage last September had taken out pretty much a lot of performance from Amazon's US East data centers. And a Gmail-related performance problem, which occurred last December, was due to the failure of two redundant network paths. In fact, these incidents are not isolated. They're getting increasingly prominent. Our analysis of high priority incidents shows that network failures can have significant impact on services. An incident is marked high priority if it can have high impact on the business or the end customer. So we analyzed this data over a period of 5 years from a large cloud provider. In this graph, the x-axis shows the type of service impacted, and the y-axis shows the percentage failures causing that particular service impact. We make two key observations out of this graph. First, connectivity loss and service errors are dominant. That is, for instance, this could lead to loss of connectivity to critical services such as health services, or users could be experiencing timeouts when they're uploading files. Second, while SLA violations are in the minority, they do risk severe customer dissatisfaction. The bottom line, however, is that network failures can significantly impact services, and understanding their root cause is a really important problem. Towards improving the dependability of the underlying systems themselves, my research has focused in three primary areas. My primary focus is on improving cloud reliability. Towards this, I have focused on studying reliability of data center networks, building automated problem inference systems, and gaining operational knowledge from deploying the systems that I built. I've also worked in other areas relating to security and privacy aspects of cloud-dependent services, specifically smartphones, and reverse engineering internet-scale systems to exploit the last bit of performance. I'd be happy to discuss these offline in case anyone's interested. In my talk today, I'll be focusing on my work on improving cloud reliability specifically. Before I get into the details, let me give you a little bit of context. This is a simplified view of a typical data center architecture, but it captures the necessary details. The data center is set as a multi-route spanning tree with rack-mounted servers at the bottom connected to top-of-rack switches or TORs. These TORs are in turn connected to upstream aggregation switches, which are then connected to layer 3 access routers or core routers. To provide fault tolerance, network elements are typically deployed in a 1:1 network redundancy pairs. Connected to the network core are a variety of other devices called middleboxes, such as firewalls, VPN devices, intrusion detection and prevention systems, and load balancers, which are used to typically distribute load across your multiple elements. Now, this is just, as I was mentioning, this is a typical configuration. Other configurations are definitely possible where you place the firewalls at different parts of the location. Now, data centers in turn are connected to each other through long-haul fiber links which run thousands and thousands of miles geographically. Let me put this figure in context of the 3 key questions that I want to answer today. First, what are the pain points in managing network infrastructure? What are the weakest links? What are the devices that fail the most in a huge architecture such as a data center? What can we learn out of them? How effective are repairs in fixing these problems? Second, consider a service operator who wants to expand their service from, say, 100 servers to 1,000 servers. Now, this boundary box here marks what is called as a network stamp, which is typically the set of elements on which a service will be sitting. So let's say you go buy some service on, say, Azure or maybe Amazon EC2. This would be the set of devices you'd be getting along with all the extra servers. So one of the fundamental questions here is, should a service operator build one single large network stamp that lowers management costs and has built-in redundancy into it, or should he build multiple smaller network stamps? If so, how many? And third, network operators, when fixing problems within data centers, use what are called as trouble ticketing systems, where they start recording problems that they observed and start writing down exactly what are the steps that they have taken to resolve problems. These are called trouble tickets. We want to analyze these trouble tickets and then see if we can reverse engineer the root causes of the network failures themselves. Why do these failures happen? And how can we learn from our mistakes to improve network management? To summarize, first, we want to find the pain points in managing network infrastructure. Given this information, we want to understand how to build highly available geo-distributed services. And finally, we also want to see if we can reverse engineer the root causes behind these network failures. Having said that, let me give you a quick glimpse of the contributions I've made in this area. My goal is to understand the reliability aspects of the underlying network infrastructure. Towards this, I have analyzed several years' worth of datasets, both structured data such as network event logs and network traffic logs, and unstructured data such as network trouble tickets as well as high severity incident reports. And towards this, I have designed and implemented several systems, some of which are listed here. One is a real-time network monitoring system, which is in deployment within a large cloud provider, monitoring tens of data centers. The second one is called NetSieve, an automated problem inference system. And third one is an analytics SDK, or a software development kit for analyzing network telemetry data. Some of these systems have been published in academic venues, and some have bagged awards. For instance, NetVisor has won the Microsoft Trustworthy Computing Reliability Award in 2013. Let me now shift gears and give you a quick walkthrough of our analysis methodology and show you how this kind of systems can actually be built. Consider two devices connected by a link. When this link goes down, an event is logged by a network monitoring system. Over the course of our observation period, we collected 25 million such events. Our goal is to use these raw events to extract what we call as impactful failures along with the problem root causes. Exactly why did they happen? Now, what makes this problem fundamentally hard are 3 key challenges. First, syslog messages, as these are conventionally called, are significantly noisy, with devices logging multiple up and down messages when they are in fact operational, or devices logging multiple up and down messages as separate messages when in fact they're down only once. So the key challenge here is how do you analyze these events and remove duplicate events out of them? Second, when a device fails, how do we know if the failure had any impact? Is it noise or did any service get impacted? And third, what was the root cause? So we can learn from our mistakes to improve both the service reliability as well as network management. Unfortunately, this information is pretty much well hidden inside these network trouble tickets that I was telling you about, and analyzing the freeform text within them is not trivial. So the way we address these three key challenges is as follows. First, in order to remove these duplicate events, we perform what is called as time-based grouping. For instance, for overlapping events, we pick the earliest of the start and end times. The intuition being that when a device has already logged that it is down, any subsequent events that say that it's down again will not matter much. Second, defining a failure is challenging in itself. For instance, look at the box on the top right. You have multiple types of devices within a data center. You have routers and switches, which could cause a loss of throughput in traffic when they fail. And you also have other types of devices like firewalls. For instance, when they're misconfigured, they do not have to cause any loss in throughput, but they could incorrectly forward traffic, thereby increasing the throughput sometimes. So in order to deal with this problem and to address these challenges, we compute two kinds of impact. One is called the traffic impact. The other one is a functional impact. Let me give you a quick glimpse of how exactly we compute the traffic impact. Consider a device through which the traffic is flowing. When the link goes down, you'd expect the traffic to go down conventionally. Well, it's common sense. Now, you have two kinds of distributions. That is, traffic that was flowing before the failure happened and traffic that has been flowing after the failure happened. Now, you may ask me a question, how can traffic flow when a failure happens? You should remember that devices not only have one interface, they have multiple interfaces. So one of the interfaces could go down, traffic could still be flowing on the other ones. So intuitively speaking, I can look at this these two types of traffic distributions and say if there is a traffic drop by say 10% or 15%, then I can say that the failure had an impact. However, one challenge there is how do you determine these thresholds? And the other challenge here is how long before the failure happened would you actually need to look at to understand the distribution of the traffic? Now, we can choose a small time window, but we risk making our method susceptible to bursty traffic. Like in data centers, we have the slash dot effect. If an article gets super famous, you pretty much get a spike in the traffic. Or you could end up choosing a large time window, but then your method would be susceptible to time of day effects and would assume long-term predictability of traffic. That is, you have some diurnal patterns, which is not true in most of the data center traffic. The way we solve this problem is by resorting to what is called as the Mann-Whitney statistical test, Wilcoxon statistical test. What we do there is we compare the median traffic flowing on the device before the failure happened to the median traffic flowing on the device during the failure. The intuition is that if this ratio is less than 1, there is impact. Now, in order to determine the right type of, the time window that needs to be considered when computing this median, what we do is we parameterize the time window, the time window size in this ratio, and then compute the accuracy. So what we are trying to test here is the null hypothesis that on a device, the traffic flowing, the distribution of the traffic flowing on the device before the failure and during the failure have identical distributions. What that means intuitively is if I am not able to differentiate the traffic values that are flowing on the device before and during the failure, then it means that I cannot use this metric for pretty much computing the impact. So this graph shows on the x-axis, it shows p-value, which is the outcome of the statistical test itself. It shows you the significance level at which you can reject the null hypothesis that they have identical distributions. The y-axis shows the distribution of the p-value. For instance, if you take that one line that is there, it is saying that in 82% of the cases, I am able to reject the null hypothesis. That is, in the other 18% of the cases, I'm not able to accurately differentiate whether there is a sufficient drop in the traffic or not. Now, you would expect, okay, now I'll start varying the time window, and that's exactly what I do. So if you take for 6 hours time window, that is before the failure happened, if I look at 6 hours, then I'm able to reject 91% of the cases, the null hypothesis in 91% of the cases. Similarly, I check for other values and figure out that 2 hours gives us the best value. That is, in 99.3% of the cases, I'm able to pretty much accurately say that, okay, now there is some kind of impact on the device because of a statistical drop in the traffic that is flowing through the device. Now, recall that what we've been looking at so far is computing traffic impact. Now, there is a whole together other beast, which is functional impact. In order to do this, what we do is we resort to my other system called NetSieve. What it is capable of doing is, if you throw a bunch of trouble tickets at it, it will automatically analyze and then extract 3 key features out of it, like problems, activities, and actions. For now, you can consider this as a black box. I promise I'll come back to this at a later part of my talk. After applying all these steps, we're left with roughly 130,000 events from where we started. So you can look at the magnitude of decrease that we achieved by applying the right set of steps and filtering these things. Now that we understand the failure analysis methodology, let us answer the key questions that I initially posed. Remember the first question we want to answer. It was concerning the pain points in the network infrastructure. Answering these questions is important to improve both service reliability as well as to build effective failure recovery mechanisms. Let us look at whether failures are uniformly distributed across devices. What I mean by this is, do different types of devices in a data center fail the same way, or do they have different behaviors? So in order to understand this, what I do is I resort to a statistical metric called the coefficient of variation. What it does is it explains the extent of variability to the mean of the population. Therefore, intuitively, all we need to understand is if this value is greater than 1 or much greater than 1, it means that the population is failing very ununiformly, like non-uniformly, in fact. So in this particular graph, we make the following observation that aggregation switches, if you can always refer to the figure on the right to understand where they fit in the hierarchy. So aggregation switches there exhibit what is called as a few bad apples effect. That is, certain devices in the population fail in a very fairly unique way. In the sense, if you're able to weed out these bad apples, you would be able to save a significant amount of time and resources. Let us see if this trend holds for middleboxes. So like I was saying, middleboxes are intrusion detection and prevention systems and all. So this graph, the x-axis shows the number of failures, y-axis is the distribution of these failures. What we observe is these IDPs, or intrusion detection and prevention systems, show the highest 95th percentile of failures. That is, these devices log approximately like 8 failures per year. This is a very high number, considering that these are the ones that protect your architecture from external attacks and all. This is something critical for you to fix first. Second, load balancers exhibit a low median value as well as a 95th percentile value of, say, 3 failures. But we found something surprising when we started digging deeper into this. So there were 3 generations, three vendors who were supplying load balancers to us. What we observed was 2 of those vendors were going through what is called again as the few bad apples effect, specifically LB1 and LB3, which are load balancer types. Now you'd be surprised if I tell you what's happening. Well, not much of a surprise because it's already listed there, but one of the things is the first generation was going through a lot of faulty power supply units, and no one really figured it out, because usually in these large data centers, they fix problems in isolation. And when one sees that a power supply unit has failed, they just go replace it in isolation, but without giving any importance to the global trends. The second problem is memory errors were pretty much getting masked by the quick fix solution of reboots. So what do you do when your laptop doesn't work? You just hit the power shutdown button and hope that it works the next time. So that's exactly what happens even in big data centers. And finally, VPNs and firewalls exhibit similar failure characteristics, except that firewalls show a very long tail of nearly 24 failures per year, which is, wow, it's kind of surprising, right? Now that I've shown you what, how these devices, what types of devices fail, let's see if these failures are significant or, they fail only for like 5 seconds or 10 seconds, in fact. So this graph shows the different types of devices on the x-axis. Y-axis shows the median time to repair. Time to repair is how long it takes for an operator to fix the problem, in fact. Observe that both aggregation switches and top-of-rack switches take a small amount of time to repair. This could happen if there are problems such as, let's say, like unexpected reloads, or there is some kind of a connection problem or a link flap or something like that. Now, access routers show a very high median time to repair. Now, if you refer to the figure on the right, you can see that access routers are positioned higher up in the hierarchy. This is extremely surprising, considering that one would expect that their problems would get fixed much faster because they are higher up in the hierarchy. And for the middle boxes, if we look at these, the x-axis again shows the time to repair in seconds, y-axis shows the distribution. What we observe is almost all middle boxes show this trend of short-lived failures. That is, they're transient failures. They occur either because the middle box has just restarted unexpectedly, or there is some kind of a connection problem in it. And we also see long-term failures which are lasting for nearly 1 to 10 days. What's happening here? Upon digging deeper, what we found was they did not have either devices in stock, or they were like really debugging a very complex software problem which they could not fix. And sometimes these can get like, I've also seen some cases where they spent 2 months in solving some problem. It was just very hard to solve the problems. And now to the most interesting question, whether repairs are being effective or not. So in this graph, the x-axis shows the type of device, the y-axis shows the probability of repair. So intuitively, lower values are better. What you observe here is that top-of-rack switches perform the best, with exhibiting about 1 in 17 devices fail. Is that good? Well, it's still relatively better compared to the other devices, like aggregation switches and access routers. Now here's where things start getting interesting. Now the probability of the second failure, given that the device has already failed and has been repaired, is, you see the trend here, right? For top-of-rack switches, the trend, there is an increasing trend that is being shown. This worsens with the third failure. We can infer 2 important observations from this. Well, access routers and aggregation switches exhibit a decreasing trend, which is very good, exhibiting that repairs are in fact being useful in this context. Top-of-rack switches show an increasing trend, implying that repairs are not quite effective in fixing problems. So one likely reason why this could happen is, if you recall, top-of-rack switches are at the bottom of the hierarchy in the data center network. Therefore, when something fails, the network operators rather prefer to replace the device or use a quick fix solution such as reboot and then get over with it. Now, these kinds of quick fix solutions can solve the problem, but it risks delaying the finding of the true problem root cause, in fact. And our findings pretty much indicate 2 important takeaways from the whole exercise. One is cost of ownership is one metric that is worthwhile exploring, not just in these systems, but any kind of security systems or anything, in fact, where you would start evaluating, does it take me more money to replace the system now versus maintaining it in the long term? Is it worthwhile for me to actually pursue this goal or not? The second one is, these kinds of data-driven approaches can be used to extract a lot of useful things, such as the effectiveness of repairs, which could be in anything, even in software systems, the effectiveness of patching a bug, in fact. Let me summarize what I have presented so far. So we've looked at the pain points in the network infrastructure. Specifically, we've seen that access routers fail the maximum fail the most, even though they are at the highest point in the hierarchy. And we've also seen the few bad apples effect being prominent in aggregation switches and middle boxes. We've also seen that these repairs were relatively more effective in access routers and aggregation switches. The surprising finding was that in top-of-rack switches, it's not quite effective at all. Let's move on to the second question. In the second question, we are interested in finding out how many network stamps does a service provider need to build in order to achieve a certain amount of SLA or a service level agreement uptime. So usually they have 3 nines or 4 nines is usually the conventional way of calling these. I'll make that clear sometime. To answer this, we need to address a more fundamental question. Is network redundancy effective in the first place or not? By now you must be getting one question in your mind. So why am I talking about failures in isolation? In these large data centers, isn't it a norm to provide another redundant device to take over whenever there is a failure? And that's exactly what we are going to discuss. Let me first explain how we compute the effectiveness of redundancy. Take this sample pair, for instance, the access routers and aggregation switches. This boundary marks what is called as the redundancy group. To compute the effectiveness of redundancy, what we do is we compare the median traffic before and during the failure across all links in this redundancy group. The intuition is that if this ratio is close to 1, it means redundancy has pretty much masked the failure totally. Now, let us look at how effective network redundancy is across different layers in the data center hierarchy. So in this graph, the x-axis indicates the network layers. The y-axis indicates the median normalized traffic. The blue bars indicate the ratio computed over individual links that are connected as I've shown here. The red bars indicate the ratio computed over the entire redundancy group itself. So ideally, if this value is 1, then I would say that the redundancy group has completely masked the failure. Therefore, individual failures don't really matter much. At the bottommost level in the hierarchy, notice that this has the most impact, but redundancy pretty much masks that failure. Inter-data center failures, that is core-to-core failures, are masked totally. Like you see that the ratio is 1. Now, one reason this could be the case is because notice that the core-to-core links are at the highest level in the topology, which means they're carrying a significant chunk of the data center traffic. So there are a lot of humans or network operators who are assigned to monitor this and make sure that they take the necessary steps to fix these problems in order to minimize service downtime. And also notice that the redundancy is least effective at the access router and aggregation switch layer. One of the potential reasons is we've also noticed that access routers exhibit the maximum failures before, right? Overall, network redundancy pretty much reduces traffic loss by about 21%. Now, having this as the result, let us see how to compute this kind of, like the architecture itself, in fact. So this is the same graph from before. In order to compute the number of independent network stamps, here's what we'll do. We'll use this equation and plug this value into R. And solving for this equation pretty much gives us how many independent network domains are needed. Therefore, if I'm a service operator and I want to provide a guarantee of 3 nines of availability, that is a maximum of about 8.7 hours of downtime per year, then I would use 3 independent L2 domains. For a guarantee of 4 nines, I would use 4 independent domains. To summarize, a service hosted on a single large network stamp risks low availability. So in fact, in order to increase the availability, build multiple smaller domains, 3 for 3 nines of availability and 4 for 4 nines of availability. To summarize, again, network redundancy is ineffective in about 33% of the cases in the network core itself, and we've also checked for these numbers as far as middle box redundancy is concerned, and it's about 33% of the cases for firewalls and load balancers. The good news for us security people is that it's nearly 100% effective for IDPS devices and VPN devices, like intrusion detection and prevention systems, for instance. And we've also seen that a service risks low availability when hosted on a single large domain, and we've also seen how to compute the number of independent network stamps. Does anyone have questions so far? Yes.
How do you infer this just for one system architecture?
We infer this for one typical architecture, which is in deployment today across a large number of cloud providers. Yes. But again, the results are dependent fairly on the data that I've analyzed. So that's one caveat with whatever my analysis is actually giving you. But what I'm going to advocate here is more of the methodology rather than the results themselves. I'm advocating that you can use a similar methodology in your settings to actually come up with such conclusions. In fact. So remember the black box that I left out initially at my talk. I was saying, well, you have a trouble ticket, you compute functional impact. This is the black box, in fact. So far, what we've been doing is we've been looking at nicely structured data. So, you have these network event logs, network traffic logs and everything, and the world has been good to us, in fact. We were able to write pretty standard statistical techniques in analyzing these things. Now, let's shift gears and come to what is called as unstructured data, the real world, where network operators are writing these trouble tickets with details of how they faced, how they fixed all these problems. In this particular talklet, I'm going to present a system called NetSieve, whose goal is to automate the problem inference from network trouble tickets to extract, say, a concise summary of the ticket itself. Let me first give you a bird's eye view of the system, and then I'll get into the details. Our goal is, given a trouble ticket, we want to extract three key features: problems, activities, and actions. Now, first, we want to know what problems were observed in the trouble ticket. For instance, did the device get stuck in a reboot loop? Did it experience some kind of, like a memory overflow bug inside it? Second, we want to also find out what kind of troubleshooting was done by the network operators. For instance, did they check for the existence of the right configuration files across the devices? Did they check for the existence of valid BGP routes, for instance? And third, finally, what was the resolution taken by the operators to fix the problem? For instance, did they replace the line card or the network card inside the device, or did they just happen to use a quick fix solution such as a reboot to fix the problem? So from each ticket, we want to infer problems, activities, and actions. Now, using these as building blocks, I want to be able to answer higher order questions. For instance, why is network redundancy ineffective? So the network redundancy itself is a very common technique that is used to mask failures. Are there cases where it fails? If so, why does it fail? Second, what are the top K failing components? Is it hardware or software, or is it that humans are making errors such as misconfigurations? And third, are new devices more reliable? So newer devices, there's one caveat, right? Newer devices can provide you with more number of features, higher capacity and all, but do they also provide you with more reliability? Are they better than their predecessors? In the later part of my talk, I'll actually show you how NetSieve is able to answer these questions. Before that, let me give you a quick overview of how a ticket looks like. This is a real ticket taken from one of the trouble ticket repositories. So tickets comprise of two fields: structured fields and unstructured fields. The top part shows the structured fields, for instance, ticket title, problem type, problem subtype, and so on and so forth. And the bottom part is the freeform text or unstructured text, in fact. This contains of operator nodes, email conversations or exchanges between operators, IM conversations, and device debug logs. So there is not really any structure that you can exploit here. Our goal is to use this information to extract three things: problems, activities, and actions. Now, what makes this problem fundamentally hard are the following challenges. First, information contained within these structured fields is coarse-grained, inaccurate, and incomplete. So in a large measurement scale, measurement study that we've done, what we found out was this was the case in 69% to 75% of the cases. So you look at the structured fields and you're like, well, what exactly is the problem? What did the operator fill in here? And the freeform text is pretty much written in natural language. So as you'd expect, lots of typos, ambiguity, grammatical errors, domain-specific words. You have no clue where to start on how to analyze these things. So to summarize, structured fields cannot be used for problem inference because of their inaccuracy. And if you do use them, you risk making the wrong decisions. And second, analyzing the freeform text itself is a challenging task. So let me show you how we answer this, achieve this part. The goal of NetSieve, the system that I built, is to understand the semantics inside a trouble ticket and give you something useful out of it. Now, in order to do this, there are two phases inside NetSieve. First, what it does is it builds what is called as a knowledge base. That is, it contains the semantic representation of the tickets on how to understand them and everything. And the second, during the operational phase, it uses some linguistic patterns to extract these three notions or the three concepts of problems, activities, and actions. Let me give you a brief, like a bird's eye view of the knowledge building phase, and then we'll look at each of the steps in detail. If I still have time. I still have time. Think of a knowledge base as a technical dictionary. So if I'm a human and if I want to do this task, what I would do? I would actually look at each and every trouble ticket. I'll go through each word, each phrase, and try to understand its semantic meaning. And that's exactly what happens in NetSieve. So once it does this, it will then use this technical dictionary, as I call it, to perform a problem inference. There are three steps to do this. In the first step, the intuition is to find the patterns that are frequently used by operators consistently across a large number of tickets. By large, well, I was lucky enough to have access to tens of thousands of these tickets. So the intuition here is that if something is failing, there are limited ways in which you could say that. For instance, here in the example shown, operators tend to use the sentences power supply unit is faulty or access router is inoperative. In the second step, given that these are the frequently occurring phrases, we want to find out which of these phrases are important in the current domain. For instance, I was working in the networking domain, so I know that certain phrases are important to me. If we're working in the security domain, then this answer changes slightly. In this step, as you can see, the first three sentences get filtered out, but the last one is to inform you that there is not really filtered out because it's pretty much useless. It's not part of the current domain, and I don't really gain much by looking at that. The third and the final step is the semantic interpretation of each and every phrase that we've already filtered out. So in order to achieve this, NetSieve resorts to what is called as ontology modeling, where it attaches a class similar to object-oriented programming to each of these phrases. Therefore, the power supply unit is tagged as what is called as an entity, and faulty gets tagged as a state associated with the power supply unit. To summarize these three steps, we first extract frequently occurring patterns, then we find out which of these patterns is important, and finally we attach a semantic meaning to each of these patterns. Let's see how this is done. So in the first step, we are interested in finding out these frequently occurring patterns. This problem, if you think about it, is equivalent to finding n-grams, where n-grams are the contiguous sequence of a series of words or sequence of words. However, when we applied standard natural language processing techniques out of the box, we faced several challenges. To begin with, they're computationally expensive. They have numerous thresholds that need to be sort of set, and it's very hard to get the right values for these thresholds. And third, not all n-grams are useful. I mean, I don't care about all the word combinations inside the trouble tickets because some of them could be noise. Our key idea is to trade completeness for speed and scalability. What we do is we utilize compression algorithms. Intuitively, if you think about it, compression algorithms, we don't really give much attention to these in the everyday thing. Compression algorithms are extremely good in exploiting the redundancy in the given input. That's how they're able to compress your given input. Therefore, the idea here is if I run the trouble tickets through this compression algorithm and then somehow tap into the dictionary that it builds, I'm able to exploit the redundancy that it finds. So once I have this dictionary, one of the drawbacks here is compression algorithms don't care about the frequency of the occurrences of these terms. So what I do is I use another algorithm called the Aho-Korsak algorithm to figure out the frequency of these terms in the original data set itself. At the end of this stage, we now have a list of repeated phrases along with their frequencies. Now, the next question is, which of these phrases are important? This is a very challenging task because how do you filter out meaningful phrases from the noisy ones? We could use an expert to do this. Well, in the first round of getting the repeated phrases, I had about 159 million phrases or something. So I could probably use maybe how many experts? Maybe 1 million experts to actually get that done or something, which is, it's obviously not scalable in fact. So what we do is we apply a pipeline of linguistic filters, which are likely to extract technical words out of the given, the repeated phrases that we extract. Then what we do is, out of the phrases that are left out, we rank them by their importance computed by information theoretic metrics. So in the table given to your right, the first 3 sentences are pretty much filtered as useful, the last 3 as noise, because they have nothing to do with networking, for instance. Out of the original 19 million phrases, by applying this pipeline, we were able to narrow it down to about a mere 5,600 phrases, which we then give to an expert for labeling. The last part is semantic interpretation. Recall that we extracted frequently occurring phrases, then we figured out which ones are important. The last step in the whole game is attaching a meaning to each of these phrases. How do we do this? How do we precisely define the meaning of each of these phrases? Well, NetSieve adopts what is called as ontology modeling. Similar to object-oriented programming, the idea here is you could categorize each of the phrases that were extracted into a certain predefined number of classes. Therefore, once these classes have been defined by an expert, now NetSieve will be able to understand how exactly to tag its given input. Some of the examples here are, I could have something called as an entity class, which could represent every object in my domain that is physically replaceable. For instance, routers, line cards are physical objects that can be replaced. So I can always call them as an entity. I could also have something called as a condition, which describes the state of an entity or an adjective, for instance. So hung state is an example where I can say the router is in a hung state. Hung state is the condition of the router. Therefore, given and replaces line card, NetSieve is able to figure out that replace is an action, line card is an entity. If all of this has confused you, let me give you an example. It should make things clear. So take an example sentence. Now, the way NetSieve analyzes this is in 3 steps. In the first step, it tokenizes the input. In the second step, it finds all domain-specific keywords inside the given input. And in the third step, it would tag each of these domain-specific words with a predefined ontology class. For instance, power LED is a replaceable entity. Amber is a condition. And similarly, you have, for instance, fiber is a physical object, so it's a replaceable entity. In the third sentence, replaced is a physical action. And this is how pretty much NetSieve pre-processes the given input. Once you have this, let me now show you how the problem inference happens. Using cues from English grammar, what we have done is we've come up with certain linguistic patterns that could be useful in actually inferring these 3 kinds of concepts, like problems, activities, and actions. The intuition here is that if an entity precedes or succeeds a problem condition, then we can carefully kind of narrow it down to saying that it's describing a problem. Let's take the previous example. Using this rule on this piece of the chunk of text, what NetSieve is able to get is that the device is in a hung state and the power supply unit is faulty. By using the rule for activities, it's able to actually extract connectivity issues have been checked and the fiber has been cleaned, and finally the power supply unit has been replaced. Now just imagine if you're able to run this in bulk over a large number of tickets, what you would be able to see is global patterns essentially on what exactly is going on. And this is exactly what we've done. Let's switch gears now and see where NetSieve has been used in the real world, in fact. So recall the first, at the beginning of this talklet, I raised some important questions like why is network redundancy ineffective? So one common view is that it could be due to misconfigurations. That's the problem behind network redundancy and all. What we found by applying NetSieve is that, in fact, the top 3 reasons are faulty cables. Second one is the least that you expect, version mismatches between two devices. This is 101 that we are taught. Well, make sure everything is in sync, but still this happens. Third is misconfigurations. Second, what are the top K failing components? We found line cards, defective memory, and supervisor engine inside these routers to fail the most. And here's where things get interesting. Are new devices more reliable? You'd expect newer devices to give you more features, give you something more, but in fact what we found out was a newer generation of access routers was found to be half as reliable as its predecessor. This one pretty much surprised the network management team. They were like, we spent an year trying to upgrade all of this. Now what is it that you're telling us, in fact? And I still remember there we told them that that's not it. We still have another finding, which is the second one here. Software bugs dominated failures in one particular class of load balancers. These bugs were mistaken to be hardware bugs. The devices were sent back to vendors saying that, hey, you know what, we are facing a problem here. Now just imagine the amount of time invested in debugging these problems and then sending it out when in fact the problem could have been fixed using a simple software patch, which could be remotely deployed by the vendor. Overall, NetSafe has proved very useful to the network management team itself in kind of extracting all these global patterns out of it. Let me summarize what we have looked in my today's talk, in fact. So we've started out at the fundamental building blocks of the data center architecture. We looked at in each and every individual device. We found out that access routers fail the maximum, and this is very surprising considering that they are higher up in the hierarchy. We also saw that given that these are the failure the characteristics of these devices, we found that hosting a service on one single large network stamp risks low availability. So we also saw how to build highly available network stamps. And finally, we also saw these root causes behind these network failures. With that, I'd like to conclude my talk, and I'd be happy to take any questions at this point. Yes.
I have another experience working with failover and redundancy and implementing redundancy. Two questions. First, as you're looking at the access routers, do you ever consider ring architecture for redundancy? Because for what I was able to see from your graphs, you have just a simple mesh architecture.
Currently, yes. I mean, what we analyzed is pretty much the deployments that follow this kind of architecture in the real world. Yes, I do.
Let me rephrase the question. Do you think that the configuration is the root cause of the flaky redundancy?
I don't think so. So one thing is the initial part of the talklet was dealing with how access routers were failing. So it does not really matter what configuration you're looking at. The second part is the effectiveness of redundancy. That's where these things kick in. But my point is of a higher order, saying that, look at these devices. They're failing like this. We don't even know what's going on behind them. And it's interesting to use these data-driven techniques to kind of deploy monitoring tools which can give you live information.
Yeah, that's true. But the idea of redundancy is, regardless of what devices fail, you have to maintain a service, right?
That is true. The surprising thing that I personally experienced is redundancy could also fail. In fact, that was the whole point of the second talklet, in saying that, well, these are not things that we as system developers admit, but in the real world, these things are happening. So,
yes.
My goal is to basically provide visibility into something that people which have not seen before, in the sense, hey, look, redundancy is also failing.
And the second question, do you play here with tickets, replacement, or do you consider the broader enterprise environment? I mean, I do have a ticket and I can parse it and I can extract the semantic part, but if my purchasing department hasn't bought the network cards, then everything falls apart, right? If I don't have on stock, for example, if I don't have a place in the rack, or if I don't have, you know what I mean?
Actually, can you elaborate on the question? I'm sorry. I didn't know.
You do working on this to improve, right?
Yes.
And you assume that you have all of the needed devices, everything that is in the stock that you can replace and all that, right? What do you consider the aspect that, all right, we know the root cause of the problem, our switch is dead, but we don't have it in the stock.
Right. Right.
And our purchasing department says that we cannot buy anything in the next week.
That is an excellent point, and I did see people saying that. So, I mean, just to confirm whatever you're saying, in the sense, for instance,
I'm saying this from a real personal
Yeah.
personal experience.
yeah, it's the same thing. I mean, I must have gone through about 1,500 tickets to actually come up with the system. So, I've also seen the exact same thing where people would complain that, well, this access router is not in stock. One of the main reasons is because it could have been decommissioned. If that's the case, then we're done. There is nothing much that can be done.
Okay,
here.
thank you.
Thanks. Any other questions?